Today we're going to talk about integration by substitution. Let's take a look at this example. What if we wanted to evaluate this integral, x squared plus 5x quantity times 4x plus 10 quantity with respect to x? So we don't have any sort of a product rule that we've discussed so far. Now, yes, what we could do in this situation would be distribute everything out, combine like terms, and then take the integration by using our basic integration rules. But let's look at a different way. Let's look at y equals x squared plus 5x. Well, then the derivative of that is 2x plus 5. And those are kind of close, aren't they? 2x, 4x, 5, and 10. It's like a multiple of 2. So let's look at y equals x squared plus 5x quantity squared. Well, then the derivative using the chain rule, bring the 2 down, leave the inside function alone, take one away for the new exponent, and then multiply by the derivative of the inside function. And now look at that 2 is there. And if we were to distribute that 2 to the 2 and the 5, we have that 4x plus 10. And this matches this exactly. So this right here, this x squared plus 5x quantity squared, is an antiderivative of this big quantity inside here. So we can see that the integral of x squared plus 5x times 4x plus 10 with respect to x is x squared plus 5x quantity squared plus our constant of integration. Okay, but how did we know to look at this? How did we figure this out? So we're going to talk about indefinite integration by substitution. Remember what our chain rule is. Our chain rule says that the derivative of a function is the derivative of the outside function, leave the inside function alone, then multiply it by the derivative of the inside function. Or another way we talked about it was that dy dx was equal to dy du times du dx, where u was that inside function. So now let's kind of work backwards from that. Let's take the integral of f of g of x times g prime of x. So we're going to let u be our inside function. So this is going to be our inside function, so this will be f at u. And then the derivative of u would be du dx, which would be g prime of x. Now look at this, u prime equals du over dx. Now remember, these aren't exactly fractions. This isn't du divided by dx in the sense that it's an actual division problem, but they do take on the same characteristics of quotients. So we could actually multiply both sides by dx to get that u prime dx is equal to du, or that g prime of x is equal to dx is equal to du. And so then we could end up substituting in, this would end up being a u, this whole thing, g prime x dx, would be a du, and then this would be something that we'd be able to integrate using the rules we've learned so far. Let's look at an example. Let's go back to that first example. X squared plus 5x times 4x plus 10 dx. So I'm going to rewrite it where I'm going to pull this 2 out here, and that's a coefficient, so I can actually bring that out. So let's look at this right here instead. All right, so we're going to pick one of these to be u, remembering that the next step is to take the derivative of u and trying to get it to match. So it makes sense to pick the one with the higher power. So we'll let u be x squared plus 5x. Then du dx, the derivative of u with respect to x, is 2x plus 5. Or if we solved for du, du would be 2x plus 5 dx. So we can replace this with u right here and replace this entire quantity here with du. And so we're going to end up integrating 2 times the integral of u du. So when we use that, this 2 is a coefficient, it carries through. That'll be u to the 1 plus 1 over 1 plus 1 plus c. But we can't leave, and now notice first of all that the 2's are going to cancel and we have u squared plus c. But we can't leave our answer in terms of u because originally we were trying to integrate with respect to x. So we need to plug back in what u is, and remember u was x squared plus 5x. And so we end up getting that the indefinite integral will turn out to be x squared plus 5x quantity squared plus c. Okay, let's see another example. Let's look at this one, the integral of 3x squared e to the x cubed dx. So what we want to do is we want to try to integrate this. So we need to think back to what our integration rules are that we know. We know that power rule, we know the rule for E, we know the rule for the natural log, and stuff like that. So we need to make this into something that we can easily integrate. And we need to try to pick it so that whatever we pick for our U, when we take the derivative, we can somehow see the derivative in there. So what we're going to do here is we're going to take this x cubed and we're going to pick that to be our U. Then the derivative of x cubed is 3x squared. So u prime, which is du over dx, is 3x squared. Solving for du, that's 3x squared dx. So here's that 3x squared dx, and here's that x cubed, and we can do our substitution. Notice I just switched these so that you could easily see that right there is going to be equal to du, and we have e to the u du. That's something that we can easily integrate. We know that the antiderivative of e to the u is e to the u plus c. And of course, we were originally trying to integrate with respect to x, so we're going to go ahead and replace our u, which our u was x cubed, and we have that the antiderivative of this 3x squared e to the x cubed dx is e to the x cubed plus c. What about this one? T cubed plus 2 over t to the fourth plus 8t minus 1. So here we have to figure out what are we going to pick as our u. Well, remember, the idea is that when we take the derivative of u, we get what's left. So it makes sense to maybe pick the one with the higher power. So we'll let u be t to the fourth plus 8t minus 1. But when we take the derivative of that, we get 4t cubed plus 8. So du would be 4t cubed plus 8 dt. But as you can see, we have t cubed plus 2 dt. They're off a little bit. They're off by a factor of 4, right? This one is 4 too big. But we could pull that 4 out, and now they would match. That t cubed plus 2 would match. But if we do that here, we need a 4 here to make it match, but we can't just put a 4 there. The only number that you can multiply by that doesn't change anything is 1. So if you want to stick a 4 there, you have to counteract that. So instead of just multiplying by a 4, we could also multiply by a 1 over 4. These canceled a 1, and I haven't actually changed my problem. The 4 is the one that I need to match my du. The 1/4 I don't need, so I can pull that 1/4 out. And now on the bottom here, you can see this matches u exactly, and on the top here, you can see that matches du exactly. So we can play that substitution game where we have this equal to 1/4 times the integral of du over u. That is something that we can easily integrate. We know that the antiderivative of du over u would be the natural log of the absolute value of u plus c. And then that 1/4 is a coefficient that will carry through. Remember, we were integrating with respect to t, so we'll have to replace that back with t, and we have that the integral that we started with turns out to be 1/4 the natural log of t to the fourth plus 8t minus 1 plus c. All right, let's take a look at this one. The integral of 5y squared times the fourth root of y cubed minus 1. So we're going to have to pick something to be our u. Now, of course, this is all being raised to the 1/4 power. So maybe what we want to do is pick what's underneath this radical, or that's being raised to a power. And if we take the derivative, that 3 would become a 2, so maybe we could make those match. So we'll let u be y cubed minus 1. Then du would be 3y squared dy. And so, unfortunately, even if I switch those around a little bit, this 5y squared dy doesn't match this 3y squared dy. So I need this 5 to be a 3. I can't just make it a 3. That would change everything. But I could multiply by a fancy 1, 1/3 times 3. That would cancel to be 1. And notice, these would cancel to be 1. I still have that 5, and I would be right back here where I started. So I haven't changed anything. But I don't need the 5, and I don't need the 1/3, so I will pull those out. And here is the 3y squared dy that I need to match du. And here is that quantity u. being raised to the 1/4. That is something that I can integrate using my little power rule, and that's going to be a 5/3 times u to the 1/4 plus 1 divided by 1/4 plus 1 plus c. So I end up getting 5/3 u to the 5/4 divided by 5/4 plus c. Now we don't divide by fractions, we multiply by the reciprocal. Notice those 5's are going to cancel, and I have 4/3 u to the 5/4 plus c, which is great, except for I was trying to integrate with respect to y, so I'm going to need to plug back in what u is, and I have 4/3 y cubed minus 1 to the 5/4 plus c. And remember, you can always take the derivative of your answer and make sure you get what we started with. Let's try another one. The integral of x times the cube root of x plus 4 dx. So as we can see here, what we talked about is we probably want to choose what's under the radical or what's all being raised to a power to be u. But the problem is that du is 1 dx. So now I have this extra x here. That's going to pose an issue. But if you look here, u is equal to x plus 4, so that means that x is equal to u minus 4, if I just subtract 4 from both sides. So if I wanted to do this type of substitution, then I would have this x would be u minus 4, and then this would be the cube root of u. Well, the cube root of u is u to the 1/3, and what I can do is distribute that u to both terms to get u to the 4/3 minus 4u to the 1/3. Now this is something that we can integrate using our power rule. That'll be u to the 7/3 divided by 7/3 minus 4u to the 4/3 divided by 4/3 plus c. Now we don't divide by fractions, we multiply by their reciprocals. Notice these 4's are going to cancel, and I'm going to need to plug back in my u. If you take the derivative of this, you will get what we started with inside the integrand, but you're just going to have to simplify it to make it match. So that turns out to be 3/7 times x plus 4 to the 7/3 minus 3 times x plus 4 to the 4/3 plus c. That's it for the indefinite integration. I'll see you next time for definite integration with substitution.